Hi there, welcome to the editorial for Biweekly Contest 32. We're going to discuss the last question now. Find longest awesome substring. Alright, so the question is simple. The idea of solving it, not so much. So we're given a string S. We want to find a substring. Now, this substring should be awesome. Awesome substring means a substring which can be converted to a palindrome irrespective of the number of swaps that you do. So basically, you pick up only the characters of the substring, arrange it as you like, and if it becomes a palindrome, then that substring, which we chose at first, is an awesome substring. So that's the idea. If this is a string given to us, we choose the substring 242, 241, then we can rearrange these as probably 24142, and that is a palindrome. So this string is an awesome substring. We found the solution. This is awesome. The code is very well compressed and there are a lot of nuances in it. So hopefully my video would help explain this well. Alright, so this question is similar to another question. Please feel free to check that out. Now, thank you, Ward Trueback. I hope that I pronounced it right for this solution. Really appreciate it. Alright, so we can. Yeah, so the way that he does it is Bitmask. I had not had any experience with Bitmasks before I checked this, so I'm gonna stress on how Bitmasks work and how has he done this. So this video is gonna be a little bit longer. All right, so the idea is if in terms of the characters and the count of characters, if the count so in this question we are going to take 10 unique characters each from 0 to 9, 0, 1, 2, 3 up to 9, so these are 10 different characters. Now the counts of characters, if all are even with the possibility of any one count being odd, then it can be a palindrome. If all are even, it's still a palindrome. If all but one are even, it can still be a palindrome. The reason being, if the count is even for any one, then you can place one here symmetrically, and you can keep doing that and exhaust um, all the occurrences of that particular digit. And one odd, because you can put that one odd digit in the center and everything else is even, so you can just symmetrically place it on both sides. So that's the idea behind it. Now the bit mask is basically this. It's a string, I could say, or whatever. So it's just a sequence of zeros and ones representing for each unique digit, each unique character, whether or not the number of occurrences of that is odd or even. So 0 represents even, 1 represents odd, and the bit mask at each position is gonna represent the odd or even nature of all the occurrences of all the digits till that point. If you don't understand this, we're gonna go over the example and hopefully you will understand it again. Understand it at that time. So as we go through the string, we track the odd even counts in our mask. If we see the same mask again, the subarray between the first position and the current position with the same mask has all the numbers in even count. Alright, so I did not understand this at the first go, so I'm going to try and spend some time explaining it. So what he says is, this is somewhat similar to prefix sum if you know that, and if you can try to relate these two, it might become easier to understand. If you don't, feel free to ignore the sentence and we'll still try to understand it. Alright, so now at each position in the string, we are having a bit mask. Bit mask is all the digits have they occurred odd number of times or even number of times. So at this place, we have a list of which digit occurred odd times, which digit occurred even times, and so on. So a bit mask represents that. Now a bit mask at ith position and a bit mask at jth position, if both of them are same, that means that each character, each unique character occurred, if it occurred even times here, then it occurred even times here. If it occurred odd times here, then it occurred odd times here. That's what same bit masks mean. Now, each digit occurrence was same whether odd or even bit at both of these places. That means that whatever came in between it. So one thing is nothing came in between them and we're talking about the same position, right? So the bit mask would be same and nothing is going to change. But perhaps there are some digits between this. How can this happen? If for any character the number of occurrences between these two positions is even, then it would remain the same, right? Because if you add an even number to an even number, it's going to remain an even number. If you're going to add a even number to an odd number, it's going to remain an odd number. So adding even occurrences would keep the odd or even nature of that count. So that's what he says. Let's read it again. If we see the same mask again, the subarray between the first position exclusive and the current position inclusive with the same mask has all the numbers that, with the even count. So the reason we do first position exclusive and last position inclusive is that first position is the counts of all the numbers till that position. So we want to check what happens afterwards. That's why we ignore the character at this position and take all the other characters. And the last position, the bitmask includes that character, so we have to include that character too. Alright, so that's what it says. I hope you're with me. If you're not, please pause the video, go back and try to understand it. If you still can't, write it in the comments below and I'll make sure to help you out. Alright, so we're clear till now. Now, what they're saying is that we'll use a DP array to track the smallest first position of each mask. So the idea here is that the number of masks is not too much. Alright, the number of masks is going to be finite and it's not too big in this case. So we used only 10 different digits, right? So 10 different digits, a mask can be, how many masks can be there? Each digit can be a 0 or 1. So each position can be a 0 or 1. It's a bit mask. So 10 places, it would be 2 possible, 2 possible, 2 possible, 2 to the power 10, right? So there can be just 1024 different bit masks possible in this scenario. That's why it would be easier for us. We'll see in the implementation how these things do matter, but yeah. So they say that we keep this DP array to keep track of the first position it occurred. Again, we'll see why that matters and everything in the code snippet below. We'll use Python 3 because I feel that's the most common language used and easier to understand. If you understand that, of course, you can just, if you're good at C, C++, you can also understand what is happening there. Note that so the idea of all these videos is the logic and not the language, not the syntax. Note that the position for 0 mask is -1 as we need to include the very first character. Again, this is a nuance which would come later. And the difference from the other question, if you've seen the other question, read it. If you don't understand it, we can discuss about it. So this is an example. Let's run through this once to update our understanding to make it more clearer. Now the string, in this case, they're only considering three characters, 0, 1, and 2. The string is 10221. The mask before we start the, iterating over the string is 000, and we do need this mask because it would yeah, so you do need this mask because okay. So let me explain one more concept before I can tell you why do we need this mask. So basically we got this bit right, that got this part right, that if we see a mask again, then all the occurrences between these two are even. But palindrome can have one digits odd, one character's odd occurrence too, right? So what we need to check is if we encounter a mask once and if we encounter anything again which is at most one digit flipped from the previous one. So that's kind of the reason we need this mask, because if let's say we hide everything other than the first character, which so S is just one. Now, if you just have the 010 mask, you have nothing to compare it with. If you have the 000 mask and you have the 010 mask, then you see that there's only a 1 bit flip between these two, and that's why this character by itself is also a palindrome. And the similar thing can also happen with other places, right? So if it's, this is just one case I'm saying, if it's all ones or if it's the whole string is a palindrome, then we need the 000 at the beginning so that we know that the whole string can be a palindrome. That's why even in prefix sum you have one extra element to denote all zeros. So that's just similar. That's why we have the 000 here. All right, moving on. So here the least significant bit, this one indicates whether or not the zero digit has even occurrences or odd. So earlier everything had even occurrences. Now one has an odd occurrence. Now 0 and 1 both have an odd occurrence. Now all of them have an odd occurrence because we encountered a 2. We encountered a 2 again, so this bit flips and this has even occurrences. Now we encountered a 1, so this middle bit flips and we have even occurrences for 1 now. So that is how the bit masks go. Now, when you encounter a 010, we do nothing. When we encounter a 011 again, so yeah, so 000, this is the first occurrence, so that's why it's marked with a black border. 010 is the first occurrence, black border. 011, first occurrence, black border. Now 111, we're not gonna, this is the first occurrence, so we can put it in a black border, but it's not needed because it's not used in the future. Now 011 is the second, has occurred before, right? So 011 can be matched with this part can become a palindrome, but 011 can also be matched with 010 because it's at most 1 bit flipped. 011 and 010 has just this bit flipped. It can also possibly be matched with 001 or 111, but we have no possible occurrences of it. We have no previous occurrences of it, so we are going to ignore that. So a palindrome can be made between these and also these. Now we move forward to 001. Now 001 does not occur before. 000, which is 1 bit differed from 001, has occurred before. So again, see, this is why it's important. If we not consider this, we not be making a palindrome of the whole string. This is because we had the first bit mask at 000, we are considering this, and that is very important, otherwise it would give a wrong answer. 011 can also be matched because it's 1 bit flipped from 001, and we can make a palindrome with this. We're not going to use this, or this because this is the longest, and that would be our solution. So that's the idea. Let's go over the code. It is very important to go over it. There are a lot of nuances in it. Now, all right. So we had been talking about the mask as a sequence of zeros and ones, right? But in the code, they have taken the mask as an integer. So they've just done the decimal representation of that binary number, which is consisting of zeros and ones. So it makes the calculations a little bit trickier to understand, but we'll do it together. RES is our solution. It's the result which we return at the end. DP, as we had seen above, is going to track the first or the smallest occurrence of each mask. Now, the index in this list DP is going to denote the mask. Again, the mask is represented as integers, and the mask, so if you think about the masks, right, we have the unique characters 0 to 10, so 0 to 9, so there are 10 unique characters. The mask will be hence of 10 digits, 10 0 or 1s, and that would be from 0 to 1023. So there are total of 1024 bit masks. That's why the length of DP is also going to be 1024, representing the location of each bit mask. We initialize the location of the first bit mask, which is all zeros, as -1, just like we did here. Now -1 has one more significance that we'll discover later. We initialize the bit mask 0th position as -1, and all the other bit masks, they've never occurred, so we set their position as length of s. Now length of s is an index which will never occur, right? If s is of length 10, setting it as 11th index, 11th is not a valid index, right? It's greater than all the indices, so that's why we set it like that. And we set it for all the other 1023 bit masks. Now what we do is we loop over all the characters in S. For each character we do this, we update the mask. Now we talked about it, it's just like updating the whether or not each digit, whether or not each character has a odd number of occurrences or even. That's exactly what we're doing. This part converts the character at the ith position, takes the ASCII of the character, subtracts 48 from it, so it converts the character to its integer equivalent. 48 is the ASCII for zeros, so that's why this would give us the integer for that particular character. So a character 6 would give us an integer 6 by doing this part just here. Now we shift 1 by that many places. So what this is doing is kind of a one-hot encoding for that number. So it's something like this. Sorry, I'm just gonna open my terminal once. Make some space here. Please ignore all of the other ones. Yeah, all right. So what is happening here is our bit mask is of this form: 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of these digits. So whenever we want to represent a number, we're representing, so we represent 0 as this, we represent 1 as this, we represent 2 as this, we represent 3 as this. So 1 followed by that many number of zeros corresponding to the number, right? So 1 followed by 0 zeros is 0, 1 followed by 1 0 is 1, 1 followed by 5 zeros is 5, and so on. So we convert this to a one-hot encoding to represent that number, and then we take a XOR with the mask. So what are we doing? The mask contains whether or not the number of occurrences of that digit is number of occurrences of that character or digit is odd or even. And whenever we encounter that particular character, we want to switch it. If it was odd, then it has become even. If it was even, then we have to make it odd. So doing a XOR with 1 at that position is going to flip it. So what we do is something like this. We had some mask, and then we are going to XOR with this. XORing with 0 is going to keep it as it is. 0 XOR 0 is 0, 1 XOR 0 is 1. So keep all the other places as it is in the bit mask, but for the number which is occurred corresponding to that number, flip the bit mask of it. So that's how the bit mask is getting updated here. Then what it does is we were allowed, so we are currently at some ith position in our string, right? Now we want to check whether or not anything has occurred in the past which can make the string ending till here a palindrome. The way we do that is we generate all the possible 10 other bit masks that can match with this bit mask. So we said that it can be at least at most 1 bit different, right? So we're gonna keep the bit mask. We're gonna check for 11 different bit masks, which is gonna be this bit mask and flipping all of the digits one by one in this bit mask, right? So the way they do that is they set j from 0 to 10, both of them included, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You get the one-hot encoding for all the numbers from 0 to 10. You do a XOR with the mask. So when you do it with 0, it's gonna flip the 0th bit. You do, yeah, the bit corresponding to 0 number. Yeah. the first bit, you could say. One, you flip the 1 bit, two, flip the 2 bit, and so on. But we just have from 0 to 9, right? We don't have a bit corresponding to 10. So, but it also does 1 shifted by 10 zeros and do a XOR with that. What would it do? It would make that highest bit, which is at the 1 followed by 10 zeros, as 1. But we do a AND with 1023. So 1023 is 0 followed by 10 ones. So if you AND it with that, it's going to remove the 1 followed by 10 zeros bit, the 11th bit. And we remove it because what we're doing is that we flip each of the digits. So from 0 to 9, we flip each of the 10 bits, and then we use the same bit mask. That's what the j equal to 10 iteration does. And this can be converted to a much longer code, which is easier to understand, but they've done this to decrease the code size, and probably it's easier to understand for people who are very experienced. So we take all the possible check masks which can match with this one which we currently have, and then what we do is we subtract the current position with the occurrence of each of these possible matching bit mask, and we update the result as max of result and the new one. So now comes the significance of initializing it with length of s. For any index, if you subtract length of s with it from it, it would be negative. And we've initialized it with 0. So if it has not occurred, then it would not update result, right? So that's what the initialization, that's the significance of it. And there's also a significance of -1. So suppose your string just consists of one character. Now the index of that one character will be 0, but whatever that one character is would be all zeros with just one in between them, right? So it would do and the one of the check masks will be all zeros, because you flip 1 bit, you will get all zeros. So we'll have I equal to 0 minus dp of all zeros, which would be -1. So that would be 0 minus -1, so that would give 1, and that's why we'll get the result 1, which is needed because one single digit is a palindrome by itself. So that's what we do here. We keep updating the result to the maximum possible palindrome which can exist. And at the end, what we do is we update the dp of mask. So that's the least occurrence of that bit mask. So we did encounter this bit mask in this ith iteration on the string, and we set this as min of the current position and the one which was already set. And that's why also this initializing it by length of s matters, because it's greater than all the positions that it can encounter, so it would keep it as minimum. So that's the idea, and at the end it just returns res. The complexity is order of nk. In our case, k is 10, so it's order of n. The reason being we iterate over all the characters, and for each character we iterate over all the possible modifications, which can be equal to the number of bits flipped plus 1, because we also check the same one, but plus 1 doesn't matter in big O complexity. So it's order of n time complexity, and memory is order of 2 to the power k. K is 10, so it's order of 1 complexity essentially, because it's not dependent on any it's not dependent on n in our particular case. So that's the explanation. If anything was unclear, please write down in the comments below and I'll help you out with it. See you. I hope this made you understand everything. Bye bye.